Okay, so we've got the recording going. Yeah, we'll give George a second. So this is our last sub-element. Have you guys thought any about when you might want to schedule the exam?
Yeah, I've gotten with George a little bit and kind of looked at my schedule. I've got 1 week where I have several jobs after work. So we were trying to figure out try to go through some of that and try to figure out a good day. I think he was kind of asking about the 6th, maybe, of November. But I'm good for most nights or weekends. It's the 4 things I had to do just happen to all be jammed up into this one particular week, which of course I don't have it in front of me, so that's not really a whole lot of help.
I know that Don, who's in charge of the VEC, said that Saturdays would probably be easier to get VEs to be able to come in and do the grading. So that's something to think about if Saturdays work well for you guys.
Well, I just got back in. Are we talking about
later,
November?
Gator, after a while,
Yeah, I'm good for the 6th or the 12th if we need to. If Saturdays are preferred, either one of those works for me.
Yeah, I think honestly the 12th, I'll have to check. I may not be available on the 12th, but that shouldn't matter. They'll be able to get other VEs in to.
I'm sorry, that'd be the 13th, the 6th of the 13th.
Okay, yeah. My oldest it's like family weekend at Southern Miss, so I think we're going up there for that. But
do we necessarily all have to take it at the same time? I mean,
no.
they give it at the club every Saturday, so if we can't make one of these, can we just, sign up for one of the other Saturdays that the club gives the test?
Yeah, I mean, in the way that the club does it, and I think it's even months, they do it on a Monday evening, and odd months, they do it on a Saturday morning. And we can always go ahead and schedule a special session, for anybody in our group. What they do is they will open it up to anybody that wants to take an exam, and they'll go ahead and they'll announce it on the website. But yeah, I mean, you don't have to take it at any particular time. If you feel like you want to spend some more time studying, then by all means do that.
I guess we can discuss.
Well, I'm going to go ahead and stop my video, and let's go ahead and we can get started. So the last sub-element, sub-element 9, antennas and transmission lines. So there's going to be 8 exam questions, and they have 8 groups under this sub-element. So the first group, basic antenna parameters, radiation resistance, gain, beam width, efficiency, and effective radiated power. So our first question, what is an isotropic antenna? That's going to be a theoretical omnidirectional antenna used as a reference for antenna gain. And if you want to relate this to something like in mechanics, it's like a point source. It's an infinitesimally small point that is going to radiate in all directions. And you know, we know it's theoretical. You can't make an antenna that small and have it work correctly, but it's used for a reference for antenna gain. What is the effective radiated power relative to a dipole of a repeater station with 150 watts transmitter output power, 2 decibel feed line loss, 2.2 decibel duplexer loss, and 7 decibel dBd antenna gain? So the ERP is going to equal the transmitter output plus the sum of the gains and losses. So we're going to start off with 150 watts. And then we need to go ahead and look at our losses. So we're going to lose 4.2 decibels. And then we're going to have 7 decibel dBd antenna gain, which is how much gain over an isotropic antenna. Well, if we go back, we know that a dipole has 2.15 decibels of gain. So this is going to be 9.15. So if we subtract the 4.2 from 9.15, we can go through and calculate that out. And we're going to come out with 286 watts. What is the radiation resistance of an antenna? That's going to be the value of a resistance that would dissipate the same amount of power as that radiated from an antenna. Which of the following factors affect the feed point impedance of an antenna? And the correct answer is antenna height. And at the lower HF bands, proximity to the ground will significantly affect the antenna feed point impedance. And you'll see this with a dipole, where the feed point impedance will vary depending on how high the dipole is, you know, above the ground. What is included in the total resistance of an antenna system? That's going to be the radiation resistance plus loss resistance. What is the effective radiated power relative to a dipole of a repeater station with 200 watts transmitter output power, 4 decibel feed line loss, 3.2 decibel duplexer loss, 0.8 decibel circulator loss, and a 10 dBd antenna gain? So what we need to do is, again, go ahead and add up our gains and losses. So we're going to have 4, 7.2, 8 decibels of loss, and 2 decibels of gain. So if we go through and do the math, we're going to come out with 317 watts. What is the effective isotropic radiated power of a repeater station with 200 watts transmitter power output? 2 decibel feed line loss, 2.8 decibel duplexer loss, 1.2 decibel circulator loss, and a 7 dBi antenna gain. So our gain is going to be 7 dBi. Since they're asking, you know, the effective radiated power, isotropic radiated power, so we're going to say that's going to be 7 decibels. And then we're going to have 2, 4.8, and 6 decibels of loss. So we're going to have 1 decibel of gain. And if you go through and calculate that out, we're going to come out with 251.7 or 252 watts. What is antenna bandwidth? That's going to be the frequency range over which an antenna satisfies a performance requirement. And generally, when you're talking about antennas, it's going to be the VSWR. And a lot of times, antenna manufacturers will state that from 2 to 1. So it'll show you, generally it'll be a dip with the VSWR, and the bandwidth is going to be those frequencies between either side where it's 2 to 1 and 2 to 1. What is antenna efficiency? And that's going to be the radiation resistance divided by the total resistance. So obviously, if the radiation resistance is higher, you're going to have a higher efficiency. Which of the following improves the efficiency of a ground-mounted quarter wave vertical antenna? And the correct answer is installing a radial system. In Louisiana, we're lucky we have fairly conductive soil, especially if you go and set up, say like on Grand Isle when it was still accessible. But even our regular soil has good conductivity. But if you install a radial system, that's going to definitely improve your efficiency. Which of the following factors determines ground losses for a ground-mounted vertical antenna operating in the 3 megahertz to 30 megahertz range? And that's going to be soil conductivity. In fact, if you look at a diagram, the U.S. Geological Survey created one back, I believe, in the 50s or 60s. And about the only area that has better conductivity, soil conductivity, than we do is the area around Kansas, which doesn't seem to make a lot of geological sense, but that's what they determined. So how much gain does an antenna have compared to a half wavelength dipole when it has 6 decibel gain over an isotropic antenna? So remember, a dipole has 2.15 dB gain over an isotropic antenna. So if your dipole has, your antenna has 6 dB gain, you need to subtract the 2.15, and that comes out to 3.85 decibels. And you could denote that as 3.85 dBi, since you're talking about the gain over an isotropic antenna. If it was talking about the gain over a dipole, it would be dBd. Okay, what term describes station output taking into account all gains and losses? And that's going to be effective radiated power. Two of the WARC bands, the 30-meter band and the 60-meter band, have stipulations in there about the effective radiated power of your station, with limitations on that. So that's where that comes in, with your band chart. Okay, our second section is antenna patterns and designs, E and H plane patterns, gain as a function of pattern, and antenna model. So in the antenna radiation pattern shown in figure E91, what is a beam width? So if you look at that, what you're going to be looking for is the 2 points where the gain is 3 dB down. So if you go ahead and you draw the lines, if you look right here, this is where it passes the negative 3 dB gain point. And it does the same down here. And you can see the angles in here. This is about 25 degrees. This is about negative 25 degrees. So your beam width is going to be 50 degrees between there. In the antenna radiation pattern shown in E91, what is the front to back ratio? So the front to back ratio is going to be the difference between the gain in the front and the gain in the back. So we can see back here, we're going to be between negative 12 dB and negative 24 dB. So they're going to go ahead and estimate it at negative 18 dB. So our difference is going to be 18 dB. In the antenna radiation pattern shown in figure E91, what is the front to side ratio? So if we look at the side, this lobe coming off here, they're going to estimate that as being negative 14 dB. So the difference between negative 14 and 0 is going to be 14 dB. Does that make good sense? I'll take that as a yes. What is the front to back ratio of the radiation pattern shown in figure E92? So we can see here that this is very close to negative 30 dB. And they're going to go ahead and say it's 28, the difference between there and 0.
Is this a vertical antenna that's showing that pattern like that, or can you assume that from the figure 9.2?
You know, just from experience, that's probably going to be a Yagi antenna because it's highly directional. And that's, you know, the purpose of, you know, a Yagi antenna is to get directionality as well as, you know, suppressing, you know, good gain, you know, front to back gain. If we were to go look on this one, you know, that's the same thing. We've got real good front to back gain as well as, you know, good front to side gain, which means when you're using that antenna, signals coming from the side are going to be quieted compared to the signals where the antenna is being pointed.
You're trying to get the minimum dB, that -3 or -4 versus the -24 is more gain on antenna.
Yeah.
You're using small negative numbers for gain.
Right. Yeah, I mean, you know, you're taught, you know, your highest point in the gain, they put that as 0, and everything else is, you know, the difference between there and the different points. So what type of antenna pattern is shown? And that's going to be an elevation pattern. What you're doing is you're looking, if you can think about the antenna, if the antenna is horizontal, this is what it's going to look like, you know, as you start tilting, you know, an imaginary arm upward. So, you know, this point here is probably about 7 degrees off horizontal. So that antenna is going to be really good for DX. DX, you want to have that elevation maximum, you know, radiation point with elevation as low as possible to get the most distance. What is the elevation angle of peak response in the antenna radiation pattern shown in figure E92? And I kind of gave that one away. That's going to be about 7.5 degrees. How does the total amount of radiation emitted by a directional gain antenna compare with the total amount of radiation emitted from a theoretical isotropic antenna, assuming each is driven by the same amount of power? And the correct answer is they're going to be the same. And you can think of
Go back-
this,
Go back one real quick. I got a question.
Sure.
On this, you're looking at degrees from maybe 0 to what, 15 to 30 and that. And are they gonna be tricky, like if the answer is 7.5, are they gonna put 7.0 or 6.5 that you need a protractor to figure this
No.
one out?
no, you won't need a protractor. The wrong answers on this one should be obvious. But kind of, talking about, the difference between an isotropic antenna and a real antenna, you can kind of think of the RF as being like a balloon, and the total volume of a balloon is going to stay the same, but you can squeeze that balloon in different points to get, a greater distance in one direction. And that's how a directional antenna is able to do that. It's not going to be able to get all of the gain in that direction, but it can get quite a bit of it.
Yagi, like blowing up a surgical glove.
Yeah, exactly. So what is the far field of an antenna? And that's going to be the region where the shape of the antenna pattern is independent of distance. The near field is when you're going to be up close to an antenna, and the modeling software that's out there for doing antenna modeling, the equations that it uses to calculate the gain in different directions is based on the far field. The near field, it's completely different and will look completely different. But when you separate the observer far enough from the antenna, the far field is what you would see if you could actually see RF. So what is the elevation angle of peak response in the antenna radiation pattern shown in figure E9-2? And we said that's going to be 7.5 degrees. Okay, we just did that. What type of computer program technique is commonly used for modeling antennas? And that's called the method of moments. And what it does, it breaks down the antenna structure into little tiny segments. And the more you can break it down, the more accurate the calculations will become. So what is the principle of a method of moments analysis? And that's where a wire is modeled as a series of segments, each having a uniform value of current. What is the disadvantage of decreasing the number of wire segments in an antenna model below 10 segments per half wavelength? And that's going to be the computed feed point impedance may not be correct. Okay, next section, practical wire antennas, folded dipoles, phased arrays, and effects of ground near antennas. So what is a radiation pattern of 2 quarter wavelength vertical antennas spaced 1/2 wavelength apart and fed 180 degrees out of phase? And that's going to be a figure 8 oriented along the axis of the array. So if you were to set this up, your gain would be in 2 directions, and that's going to be along that imaginary line drawn between the 2 antennas. What is a radiation pattern of 2 quarter wavelength vertical antennas spaced a quarter wavelength apart and fed 90 degrees out of phase? And that's going to be a cardioid. And this type of phased array can be useful when you're trying to silence out noise. So what you would do is you would point this section to where the noise is, and that would silence it out because you can see it's got that deep null in there. It's also very useful for identifying where you're getting RFI coming from.
That must be for constant sources of noise, right? Because you're not going to have two vertical antennas that you can rotate on demand.
Shorter ones you could say, like if you were looking at like 70 centimeter noise that you were finding there.
You could set them up on a rotating something or other.
Yeah.
Okay.
Generally, what's more often used is a loop, because it has it's not as good as a cardioid as far as having a single dead spot, but it does have two dead spots, and it makes it useful for hunting down the RFI. In fact, I've kind of halfway started building one. Not that I've got an RFI problem, but you figure it's a nice little thing to have in your handbag. What is a radiation pattern of 2/4 wavelength vertical antennas spaced a half wavelength apart and fed in phase? So now it's going to be a figure 8, but it's going to be broadside of the axis drawn between the two antennas. And that's completely due to the fact that they're fed in phase. If we went back, when they're 180 out of phase, that changes the direction. So you could potentially use these two antennas, and switch between in and out of phase to go ahead and change the direction that you're, trying to communicate on. What happens to the radiation pattern of an unterminated long wire antenna as a wire length is increased? And the correct answer is the lobes align more in the direction of the wire. Which of the following is a type of off-center fed antenna? And that's going to be a dipole fed approximately 1/3 of the way from one end with a 4-to-1 balance to provide multiband operation. And that's commonly called the Wyndham antenna. And in reality, there's a lot of discussion about is 1/3 of the way from one end, the correct distance. And people have done some experimentation and have kind of optimized it a little bit, but that's beyond what we're doing. What is the effect of adding a terminating resistor to a rhombic antenna? And that's going to change the radiation pattern from bidirectional to unidirectional. And you can see here the radiation pattern. A rhombic antenna really has a lot of gain, and front to back ratio is amazing, front to side ratio is amazing, but they take up an awful lot of space for HF. But you can build one for UHF VHF that would potentially be handheld. What is the approximate feed point impedance at the center of a 2-wire folded dipole antenna? And that's going to be 300 ohms. And the figure down here shows you what a folded dipole looks like. It's going to be a half wavelength, and it's going to come back on itself. And that feed point is going to be 300 ohms.
Is that affected by height or that not, not,
No, that there's probably a small effect with height, but this is more in general. It's going to be a 300 ohm feed point. So our next question is, what is a folded dipole antenna? It's a half-wave dipole with an additional parallel wire connecting its two ends. And I have never actually seen one of these, although they do have a variant that's used in emergency communications. Way to think about it is that it's equally bad on all frequencies, but it'll tune up on a very broad range of frequencies. So if you're operating, on a ham band, it will work. May not work very well, but it'll work. Or if you're doing Mars operations when you're on military frequencies, it'll work on those frequencies as well. Which of the following describes a G5 RV antenna? So G5 RV, it's a multi-band dipole that's fed with coax and a balun, and it's going to go through a selected length of open wire transmission line. And you can see that here. This is
got one of those in my attic for the 40 meter, and it's not 51 feet, it's smaller, but it has the 34 feet of the open line.
And so it's like a G5 RV Junior.
Yeah, right. Except it doesn't do 80.
Yeah, hold on just a second. I got a request to send send the meeting link. Yeah, so they do make what they call a G5 RV Junior that is smaller. Which of the following describes a ZEP antenna? And that's going to be an end-fed dipole. And where these were popular were on, on Zeppelins back, pre-World War II and World War II. They would go ahead and have, a trailing line behind the Zeppelin, and they use that as their antenna. How is the far-field elevation pattern of a vertically polarized antenna affected by being mounted over seawater versus soil? And the correct answer is the low angle radiation is going to increase. And that's because the conductivity of seawater is much higher than soil. So you can imagine if you're out in a sailboat, you're going to get really good DX as compared to, somebody, sitting on land.
Put radios in.
Which of the following describes an extended double ZEP antenna? And that's going to be a center-fed 1 1/4 wavelength antenna. It's got two 5/8 wave elements fed in phase. And they're usually, they use a impedance matching section of balance feed line. I know MFJ sells extended double ZEPs. I honestly don't know anybody that's ever used one, but it is a well-known antenna. How does a radiation pattern of a horizontally polarized 3-element beam antenna vary with increasing height above ground? And the takeoff angle of the lowest elevation lobe decreases. So basically what that's telling you is that the higher you can get your 3-element beam, the lower the takeoff angle is going to be. How does the performance of a horizontally polarized antenna mounted on the side of a hill compared with the same antenna mounted on flat ground? And the correct answer is the main lobe takeoff angle will decrease in the downhill direction. So not all is lost if you live on a hill. So our next section, Yagi antennas, parabolic reflectors, circular polarization, loading coils, top loading, feed point impedance of electrically short antennas, antenna Q, and RF grounding. So how much does the gain of an ideal parabolic dish antenna change when the operating frequency is doubled? And that's going to be 6 dB. How can linearly polarized Yagi antennas be used to produce circular polarization? And you can do that by arranging 2 Yagis perpendicular to each other with the driven elements at the same point on the boom and feeded 90 degrees out of phase. Where should a high Q loading coil be placed to minimize losses in a shortened vertical antenna? And that's going to be near the center of the vertical radiator. If you ever look at a lot of mag mount antennas, they'll have a little coil twist in them about the center of that antenna. And that's to minimize the losses. Why should an HF mobile antenna loading coil have a high ratio of reactance to resistance? And that's going to be to minimize losses. What usually occurs if a Yagi antenna is designed solely for maximum forward gain? And that's going to be a reduction of the front to back ratio. And the front to side ratio will probably be affected as well. But front to back ratio is the answer they're looking for. What happens to the SWR bandwidth when one or more loading coils are used to resonate an electrically short antenna? And that's going to decrease the bandwidth. What is an advantage of using top loading in a shortened HF vertical antenna? And that's going to be improved radiation efficiency. What happens is the Q of an antenna increases. And the correct answer is the SWR bandwidth decreases. So Q is basically a value that kind of describes how wide or narrow that SWR bandwidth is. So if the Q is high, the bandwidth is going to be very narrow. A good example of that would be a magnetic loop. It's a very high Q antenna. The SWR bandwidth is very, very narrow. So if you're using it and you decide to change frequencies, you need to retune the antenna to move that within the range that you're trying to operate on. What is the function of a loading coil used as part of an HF mobile antenna? The correct answer is to cancel capacitive reactance. What happens to feed point impedance at the base of a fixed length HF mobile antenna when operated below its resonant frequency? And the radiation resistance decreases and the capacitive reactance increases. Which of the following conductors would be best for minimizing losses in a station's RF ground system? And that's wide, flat copper strap. And if you look at the clubhouse, that's what we have on the outside going to our grounding system is wide, flat copper strap. Which of the following would provide the best RF ground for your station? And that's going to be an electrically short connection to 3 or 4 interconnected ground rods driven into the earth. Our next section, matching antennas to feed lines, phasing lines, and power dividers. What system matches a higher impedance transmission line to a lower impedance antenna by connecting the line to the driven element in 2 places, spaced a fraction of a wavelength each side of the element's center? And that's going to be a delta match. And that's used a lot with Yagi antennas. What is the name of an antenna matching system that matches an unbalanced feed line to an antenna by feeding the driven element both at the center of the element and a fraction of the wavelength to one side of the center? And that's going to be the gamma match. And I've actually got a 5-element 6-meter Yagi in my backyard that has a gamma match. What's nice about a gamma match is that your driven element doesn't need to be cut. It can be a solid section of aluminum. You don't need to, cut it and try to support it in multiple places. And what they use a lot of times for the matching section is a piece of aluminum, and what they do is they feed the inner shield of coax in there. And by adjusting how far away that section is and how much of the inner shield of the coax is inside there, will change the capacitance of it. And you can adjust that to where you get a perfect match. And I've actually modeled mine with some modeling software, and from 50 megahertz to 51 megahertz, the SWR is almost perfect 1-to-1.
What is that? Oh, I'm sorry, Chris.
Go ahead.
I was going to ask, what is that distance on yours?
The distance between the driven element and the capacitance tube is like an 1.25 inches. The length of the tube is, say, about 14 inches. So, for 6 meters, that works out really, pretty well. I've never tried to calculate one for, a lower band like 10 meters or 20 meters. But I imagine that it would probably scale similarly. To kind of give you an idea, the element itself is probably about 6 feet long total.
Okay.
So what is the name of the matching system that uses a section of transmission line connected in parallel with the feed line at or near the feed point? And that's going to be a stub match. And, a stub match, can come in very handy when you're, you've got a monoband antenna and you don't want to go ahead and try to set up a very complicated matching system. A stub match works really well for that.
How do you determine if it's shorted or opened?
Yeah,
Yeah, I saw that on the last question.
for these, you know, what you're talking about is more when you're talking about using stubs for filters. For these, it's going to be a continuous loop where you're connecting both sides of the antenna to each other.
But they say in the discussion that they consist of a shorted or open segment of line. How do you determine which one you use?
Well, you know, for that, you know, you can actually use those for bandpass filters. And depending on what you're trying to filter out, if you're trying to make it a notch filter or a bandpass filter, you'll go through and they've worked out, not only whether you want a shorted or an open, but how long it needs to be, for each band. What is the purpose of the series capacitor in a gamma type antenna matching network? And that's to cancel the inductive reactance of the matching network. How must an antenna's driven element be tuned to use a hairpin matching system? And the driven element reactance must be capacitive. And if you've ever made a handheld direction finding Yagi with tape measure, they usually use a hairpin match to match the two sides of the driven element. Which of these feed line impedances would be suitable for constructing a quarter wave Q section for matching a 100 ohm loop to a 50 ohm feed line? That's going to be a 75 ohms or RG11 or RG6. RG6 is what they use for your cable TV and your cable internet service. RG11 is more in size with RG58. The downside of doing that is that if you were to say try to match a loop with a balun, it can be used on multiple bands. With a quarter wave matching section, it becomes monoband. So what parameter describes the interactions at the load end of a mismatched transmission line? And that's going to be reflection coefficient. And that's going to tell you how much of your signal is going to be reflected because of the impedance discontinuity. So obviously, the closer you can get the impedance to, 50 ohms real and 0J, the lower reflection coefficient you're going to get. What is the use for a Wilkinson divider? And a Wilkinson divider is used to divide power equally between two 50 ohm loads while maintaining 50 ohm input impedance. And a good example of where you might use this, say you're a long distance trucker and you want to put 202 inch whip antennas on your mirrors. Well, you'd want to use a Wilkinson power divider to connect those two antennas together to go back to your radio to minimize any mismatch. Which of the following used to shunt feed a grounded tower at its base? And that's going to be a gamma match. Which of these choices is an effective way to match an antenna with a 100 ohm feed point impedance to a 50 ohm coaxial cable feed line? And that's going to be to insert a quarter wavelength piece of 75 ohm coax transmission line in series between the antenna terminals and the 50 ohm feed cable. What is the primary purpose of phasing lines when used with an antenna having multiple driven elements? And that's to ensure that each driven element operates in concert with the others to create the desired antenna pattern. So you remember we talked about those two verticals, and depending on whether the signal was in phase or out of phase would greatly affect the antenna pattern. It would basically rotate it 90 degrees. So that's that primary use of phasing lines. All right, next section. Transmission lines, characteristics of open and shorted feed lines. That's something that we were talking about earlier, Mike. Coax versus open wire, velocity factor, electrical length, coax cable dielectrics. So what is the velocity factor of a transmission line? And the velocity factor is going to be the velocity of the wave in the transmission line divided by the velocity of light in a vacuum. So we know you can never go faster than the speed of light in a vacuum, but you can go slower when you're going through media. And, you know, for a transmission line, generally what you're looking at a lot of times, say with coax, let's see, now I don't have my camera on, but, you know, most coax, a lot of times, the velocity factor is around 0.66, which means that the wave, electromagnetic wave, travels about 2/3 the speed of light through the transmission line. Which of the following has the biggest effect on the velocity factor of the transmission line? And that's going to be the dielectric materials used in the line. Generally, the dielectric material, it's a non-conductor, but it can be either solid or foam. And you know, a solid and a foam dielectric will have different velocity factors. Why is the physical length of a coaxial cable transmission line shorter than its electrical length? And that's because, as we had mentioned, electrical signals move more slowly in a coaxial cable than in air. What impedance does a half wavelength transmission line present to a generator when the line is shorted at the far end? And that's going to be a very low impedance. And Mike, this is that chart that will, it shows you, you know, what the stub is going to look like based on whether or not it's shorted or open and the length of the stub.
So the length is telling you whether to open it or short it. If you're using a shorted stub, is that when it says like the quarter wave says open and the half wave says shorted?
Right.
It's short.
Yeah. So depending on what you're looking for, you know, if you're looking for a short, an open, you know, a quarter wave open stub will get you that, where if you use a shorted stub, you're going to have to go to a half wavelength.
Okay, that's how you read it.
Yeah.
Okay. So you're gonna want either the shorted or the open, and you have to go to the chart to figure out how to get it.
Correct. Correct. What is the approximate physical length of a solid polyethylene dielectric coaxial transmission line that is electrically a quarter wavelength long at 14.1 megahertz? So a solid polyethylene dielectric has a velocity factor of 0.66. So we can go in and calculate the wavelength at 14.1 megahertz in free space. So that's going to be about 5.319 meters. So if you multiply that by 0.66, that's going to be 3.51 meters, or about 3.5 meters. What is the approximate physical length of an air insulated parallel conductor transmission line that is electrically a half wavelength long at 14.1 megahertz? And they show the calculation down here. How does ladder line compare to small diameter coaxial cable such as RG58 at 50 megahertz? And that's going to be lower loss. If you look at a loss versus length chart, ladder line is always going to be a much lower loss. So if you ever, I would, suggest taking a look on YouTube, and they show some of these great big antennas that are used for shortwave stations, where they're trying to broadcast all over the world. They're all being fed with ladder line. They usually use 600 ohm ladder line, but you won't see coax in there at all. It's all ladder line, all because of the losses. Which of the following is a significant difference between foam dielectric coaxial cable and solid dielectric cable, assuming all other parameters are the same? And our correct answer is going to be all of these choices. The foam dielectric is going to have a lower safe operating voltage limit. It's going to have a lower power loss per unit length, and it's going to have a higher velocity factor. What is the approximate physical length of a foam polyethylene dielectric coaxial transmission line that is electrically 1/4 wavelength long at 7.2 megahertz? So we can go in and calculate this. So that quarter wavelength is going to be 10.416 meters. And if we multiply it by 0.66, we get 6.875. Correct answer is going to be 6.8. What impedance does a 1/8 wavelength transmission line present to a generator when the line is shorted at the far end? And that's going to be an inductive reactance. What impedance does a 1/8 wavelength transmission line present to a generator when the line is open at the far end? And that's going to be capacitive reactance. What impedance does a 1/4 wavelength transmission line present to a generator when the line is open at the far end? And that's going to be a very low impedance, or short. And what impedance does a 1/4 wavelength transmission line present to a generator when the line is shorted? And that's going to be a very high impedance, or open. Okay, the Smith chart. And if you have a nano VNA, a nano VNA will draw a Smith chart for you. So which of the following can be calculated using a Smith chart? And that's going to be impedance along transmission lines. What type of coordinate system is used in a Smith chart? And that's going to be resistance circles and reactance arcs. Which of the following is often determined using a Smith chart? The correct answer is impedance and SWR values in transmission lines. What are the two families of circles and arcs that make up a Smith chart? And that's going to be resistance and reactance.
telling us the Smith chart's telling us that we could have a certain length of coax cable going to antenna, and if it's not the correct length, then we're gonna have nothing getting into the antenna, all coming back to the radio.
Yeah, it'll show you what the reactance will be. Generally, reactance, you're trying to avoid that with the antenna because that gets, that power, gets, converted to heat. It doesn't go out.
Are we talking a transmission line? Or are we talking the antenna? It looks like it's telling me that the impedance and SWR values in the transmission line are affected by its length, according to what the Smith chart says.
Yeah, it can be depending on the type of transmission line that you're using.
Okay, that's the key then. It may be different with the twin lead. It may be different with a coaxial cable.
Yes.
Okay.
Exactly. So which of the following is a common use for a Smith chart? And that's going to be to determine the length and position of an impedance matching stub. So on the Smith charts shown in figure E9.3, what is the name of the large outer circle on which reactance charts terminate? And that's going to be this circle. And that's going to be the reactance axis. On a Smith chart shown, what is the only straight line that's shown? And that's going to be the resistance axis. So this right down the middle, that's going to be your resistance axis. So when you're looking at a match of 1-to-1, you want to see it right there at 1.0. That way you know that you have 50 ohms resistance and no reactance. So it's basically a perfect match. So next question. What is the process of normalization with regard to a Smith chart? And that's reassigning impedance values with regard to the prime center. What third family of circles is often added to a Smith chart during the process of solving problems? And that's going to be standing wave ratio circles. What do the arcs on a Smith chart represent? And that's going to be points with constant reactance. How are the wavelength scales of a Smith chart calibrated? And that's going to be in fractions of transmission line electrical wavelength. And I believe this is our last section. Receiving antennas, radio direction finding antennas, Beveridge antennas, specialized receiving antennas, and long wire receiving antennas. When constructing a Beveridge antenna, which of the following factors should be included in the design to achieve good performance at the desired frequency? And the correct answer is that it should be one or more wavelengths long. So to put up a Beveridge antenna, you're going to need some property, quite a bit of property. Which is generally true for low band, and by low band, 160 and 80 meter receiving antennas. And that is that atmospheric noise is so high that gain over a dipole is not important. What is the receiving directivity factor? And that's going to be the forward gain compared to the average gain over the entire hemisphere. And that's a value that's used to determine the merit of a radio receiving antenna system. The higher that RDF is, the more directional the antenna is going to be. What is an advantage of placing a grounded electrostatic shield around a small loop direction finding antenna? And that's to eliminate unbalanced capacitive coupling to the surroundings, and that'll improve the nulls. What is the main drawback of a small wire loop antenna for direction finding? And that's that it has a bidirectional pattern. Unlike a cardioid, which has that single null, a small wire loop is going to have two nulls. What is the triangulation method for direction finding? And that's where antenna headings from several different receiving locations are used to locate the signal source. So what you'll end up doing is trying to determine, which direction that signal is coming from. And what you'll do is you'll be able to draw it. So it could be anywhere along that line. And then you're going to move and listen for the signal again. And you'll be able to draw that another line through. And generally, you'll probably want to add a third that may go through to help you pinpoint exactly where the transmitter is located. So that's part of what they call a fox hunt. Why is RF attenuation used when direction finding? And that's to prevent receiver overload, which reduces pattern nulls. Generally with a fox hunt, the transmitter is very, very low power. But as you get closer to it, that power is enough to go ahead and overwhelm the receiver portion of the radio that you're using. So what a lot of people will do is they'll put a RF attenuator in there to lower that so it doesn't overload the radio. What is the function of a sense antenna? And that's to modify the pattern of a direction finding antenna array to provide a null in one direction. What is a pennant antenna? A pennant antenna is a small vertically oriented receiving antenna consisting of a triangular loop terminated in approximately 900 ohms. And a pennant is used when you don't have room for a beverage, which if you live in the city, a pennant might be an option. How can the output voltage of a multiple turn receiving loop antenna be increased? And that's done by increasing the number of turns and or the area. What feature of a cardioid pattern antenna makes it useful for direction finding? And that's the very sharp single null. And that is it. That was a rather long section, but we'll make do. So let's go through and go through our practice questions. And of course, my login would expire. And of course, it needs two-factor authentication. Yes, 30 days. Come on. You can do it. Okay. So what is an isotropic antenna?
D.
Yeah, theoretical. What is the effective radiated power relative to a dipole of a repeater station with 150 watt transmitter output, 2 dB feed line loss, 2.2 dB duplexer loss, and 7 dBd antenna gain?
C, Charlie.
Yeah. Let me see. What is the radiation resistance of an antenna?
It is the B, Bravo.
Yeah, Bravo. Which of the following factors affect the feed point impedance of an antenna?
B.
B.
Yeah, antenna height. What is included in the total resistance of an antenna system?
Delta. D, Delta.
C.
What is the effective radiated power relative to a dipole of a repeater station with 200 watts transmitter power output, 4 dB feed line loss, 3.2 dB duplexer loss, 0.8 dB circulator loss, and a 10 dBd antenna gain?
A.
A.
Yeah, alpha. What is the effective isotropic radiated power of a repeater station with 200 watts transmitter output power, 2 dB feed line loss, 2.8 dB duplexer loss, 1.2 dB circulator loss, and 7 dBi gain?
C.
Yeah, C. What is antenna bandwidth?
B.
B.
Yeah, B. What is antenna efficiency?
C.
Yeah, C. Which of the following improves the efficiency of a ground-mounted quarter wave vertical antenna?
Like in Baker.
Put your radials in.
Yes.
Which of the following factors determines ground losses for a ground-mounted vertical antenna operating in 3 to 30 megahertz range?
B.
Yeah, soil conductivity. How much gain does an antenna have compared to a half-wave dipole when it has 6 dB gain over an isotropic antenna?
A.
A.
Yeah, that's going to be 6 minus the 2.15. What term describes station output taking into account all gains and losses?
C.
D, Delta.
Yeah, I heard D, delta. In the antenna radiation pattern shown in figure E91, what is the beam width?
B,
D delta.
Dog.
Yeah, it's going to be D. Remember, the beam width is going to be the angle between the 2 points where it's 3 dB down. So that's about 25, negative 25. That's about positive 25. So 50. So what is the front to back ratio?
I think it was on that one.
I heard 18? Yeah,
Yeah, 18.
yeah. This is about approximately 18 there. Okay, what is our front to side ratio?
That's gotta be C.
Yeah, it's about 14. Closer to 12 than 24. All right, what is our front to back ratio on here?
B,
B.
Yeah, that's going to be about 28. What type of antenna pattern is shown?
Elevation.
elevation D,
Yeah, elevation. What is the elevation angle of peak response in the antenna radiation pattern shown?
7.5. Charlie.
Yeah, that's 7.5. That's about 15. So that's about 7.5. How does the total amount of radiation emitted by a directional gain antenna compared to the total amount of radiation emitted from a theoretical isotropic antenna, assuming each is driven by the same amount of power?
That's the alpha. A.
D delta.
No, let's see. No, I think it's radiation B A.
D,
It's going to be delta.
Yeah.
They're both going to be the same. The only thing with the directional antenna is that, remember, it's like a balloon. You know, you're squeezing that RF to go in a particular direction, but the total amount is always going to be the same. What is the far field of an antenna?
D Charlie.
it's gonna be D,
Yeah, it's going to be where the antenna pattern is independent of distance. What type of computer program technique is commonly used for modeling antennas?
B,
B like in Baker.
Yeah,
Bravo.
method of moments. What is the principle of a method of moments analysis?
Charlie.
Charlie. C.
Yeah, Charlie. What is the disadvantage of decreasing the number of wire segments in an antenna model below 10 segments per half wavelength?
B,
So I think that's C.
Yeah, it's gonna be C. What is the radiation pattern of two quarter wavelength vertical antennas spaced 1/2 wavelength apart and fed 180 degrees out of phase?
A.
D, like dog.
Yeah, it's gonna be A. What is the radiation pattern of two quarter wavelength vertical antennas spaced a quarter wavelength apart and fed 90 degrees out of phase?
D, delta.
Yeah, this is gonna be the cardioid. What is the radiation pattern of two quarter wavelength vertical antennas spaced a half wavelength and fed in phase?
B,
B.
Yeah, it's gonna be broadside. What happens to the radiation pattern of an unterminated long wire antenna as the wire length is increased?
B. Bravo.
Yeah,
B.
they're gonna align in the direction of the wire. Which of the following is a type of off-center fed dipole antenna?
so A,
Yeah, alpha. What is the effect of adding a terminating resistor to a rhombic antenna?
That's A.
Yeah, that's going to be A. What is the approximate feed point impedance at the center of a two-wire folded dipole antenna?
A,
As well.
Yeah, 300 ohms. What is a folded dipole antenna?
D, delta.
delta,
Delta. Which of the following describes a G5 RV antenna?
C.
Yeah, C.
C,
Which of the following describes a ZEP antenna?
B, bravo.
Yeah, Bravo.
B, yeah, B,
How is the far field elevation pattern of a vertically polarized antenna affected by being mounted over seawater versus soil?
Charlie,
Charlie,
Charlie. Which of the following describes an extended double ZEP antenna?
That's C also.
Yeah. Also, how does the radiation pattern of a horizontally polarized 3-element beam antenna vary with increasing height above ground?
B.
Yeah, the takeoff angle is going to decrease. How does the performance of a horizontally polarized antenna mounted on the side of the hill compare with the same antenna mounted on flat ground?
A alpha.
I think it's D, delta.
B.
I think it decreases in the damage.
Yeah. It decreases.
All right, that's as far as I studied on my own today. I'm useless for the rest of the quiz.
How much does the gain of an ideal parabolic dish antenna change when the operating frequency is doubled?
It's A.
Yeah,
A.
6 decibels. How can linearly polarized Yagi antennas be used to produce circular polarization?
A.
Yeah, that's going to be A. Where should a high Q loading coil be placed to minimize losses in a shortened vertical antenna?
It's D dog.
D.
Yes, center.
Near the center. Why should an HF mobile antenna loading coil have a high ratio of reactance to resistance?
B.
Bravo?
I think it's A.
Yeah, I think it's A as well.
Yeah, losses.
What usually occurs if a Yagi antenna is designed solely for maximum forward gain?
B.
B, yeah, bravo.
You're going to lose out on front
Yeah.
to back ratio.
Ratio decreases.
What happens to the SWR bandwidth when one or more loading coils are used to resonate an electrically short antenna?
A.
Anybody else for A?
I guess no. I don't know.
It's going to decrease the bandwidth. What is an advantage of using top loading in a shortened HF vertical antenna?
Well, it's either A or B.
B.
A. What happens as the Q of an antenna increases?
B.
Yeah, it's the bandwidth is going to decrease. What is the function of a loading coil used as part of an HF mobile antenna?
C.
Yeah, the coil is going to act like an inductor, and we want to use that to cancel capacitive reactance. What happens to feed point impedance at the base of a fixed length HF mobile antenna when operated below its resonant frequency?
B,
C.
bravo.
C.
Yeah. I heard Bravo. So let's look at this. You know, when you're feeding it below its resonant frequency, it's not going to work as efficiently. So that means that the radiation resistance is going to decrease. So that takes us to either A or D. So if radiation resistance decreases, that means reactance has to increase. So it's going to be A. Which of the following conductors would be best for minimizing losses in a station's RF ground system?
A,
Yeah, flat wide copper strap. Which of the following would provide the best RF ground for your station?
See,
it's gonna be C.
Yeah, C. All right, we're rocking and rolling. What system matches a higher impedance transmission line to a lower impedance antenna by connecting the line to the driven element in two places spaced a fraction of a wavelength each side of the center, element center?
so that's D.
B,
Yeah, delta match. What is the name of an antenna matching system that matches an unbalanced feed line to an antenna by feeding the driven element both at the center and at a fraction of the wavelength to one side of the center?
Is that D, delta?
Yeah,
C,
it's gonna be a gamma match.
That's the one you have, right, Chris?
Yeah.
Yeah.
What is the name of the matching system that uses a section of transmission line connected in parallel with the feed line at or near the feed point?
That's A.
A,
Yeah, a stub match. What is the purpose of the series capacitor in a gamma type antenna matching network?
C.
Yeah,
So-
we're going to put a capacitor in to cancel the inductance. How must an antenna's driven element be tuned to use a hairpin matching system?
C,
Anybody else for C?
Yeah, I'll go with C.
And
B.
it's A.
Oh.
Which of these feed line impedances would be suitable for constructing a quarter wave key section for matching a 100 ohm loop to a 50 ohm feed line?
That's D.
B, D,
Yeah, 75 ohms. What parameter describes the interactions at the load end of a mismatched transmission line?
B,
A alpha.
Yeah, it's going to be reflection. What is the use for a Wilkinson divider?
That's A.
I'd say A alpha.
A, yeah,
Yeah, it's A. Which of the following is used to shunt feed a grounded tower at its base?
D.
Yeah, it's going to be a gamma match. Which of these choices is an effective way to match an antenna with a 100 ohm feed point impedance to a 50 ohm coaxial feed line? Okay, you
D.
kind of saw this before. We had 100 ohms and we're trying to transform to 50.
D,
See,
Yeah, so a quarter wavelength of 75 ohm in series. What is the primary purpose of phasing lines when used with an antenna having multiple driven elements?
B,
Yeah, that's an B.
B,
All right, we're rapidly coming to the end. What is the velocity factor of a transmission line?
Alpha.
A, yeah.
Yeah. Which of the following has the biggest effect on the velocity factor of a transmission line?
That's alpha as well.
A,
Yeah,
So, yeah.
the dielectric material. Why is the physical length of a coaxial cable transmission line shorter than its electrical length?
A again.
Alpha.
alpha,
What impedance does a half wavelength transmission line present to a generator when the line is shorted at the far end?
E,
B, B. No,
It's A. Alpha.
Unfortunately, these are ones you're gonna kind of have to memorize. What is the approximate physical length of a solid polyethylene dielectric coaxial transmission line that is electrically 1/4 wavelength long at 14.1 megahertz?
D,
A,
yeah, it's at 5 point. A. Stick with D.
well, remember, it should be shorter than a quarter wavelength. So I think C. What is the approximate physical length of an air insulated parallel conductor transmission line that is electrically a half wavelength long at 14.1 megahertz?
B,
So we know quarter wavelength is going to be about 5 meters. Half wavelength is going to be about 10 meters. And parallel conductor transmission line, the velocity factor is close to 0.9. So I'm going to say
D.
D. And I'm wrong.
Nope.
Oh, no. Is it D? Yep, it's C.
10.
How does ladder line compare to small diameter coaxial cable such as RG58 at 50 megahertz?
Be like Charlie, small reflecting coefficient.
Well, remember the reflection coefficient is going to, that includes the antenna.
It's not it.
Is it lower loss?
Yeah, lower loss. Which of the following is a significant difference between foam dielectric coaxial cable and solid dielectric coaxial cable, assuming all the other parameters are the same?
That's A.
A,
Yeah, this is our all choices. What is the approximate physical length of a foam polyethylene dielectric coaxial transmission line that is electrically a quarter wavelength long at 7.2 megahertz. So quarter wavelength is going to be about 10.5 meters. And our velocity factor is going to be 0.66. So I'm going to say what looks pretty close is 6.9. And I'm wrong. And I'm wrong again. 8.3. What impedance does a 1/8 wavelength transmission line present to a generator when the line is shorted at the far end?
Like Bravo?
Yeah, this is another one you're going to have to memorize.
No, it's inductive,
Inductive. Yeah.
not capacitive.
When it's open,
It's capacitive.
capacitive.
Yeah.
Okay, so quarter wavelength open. Yeah, we know it's going to be Charlie or Delta. Anybody want to take a swing?
I say C, Charlie.
C.
Yeah, all right, we got it.
Yeah, because you think it's open, it's gonna be high impedance, but it's actually shorted. Or, actually a short impedance.
So if it's shorted, then we know it's got to be very high. All right.
Do all that stuff with the calculation, the wavelength and the quarter wave, the frequency and the quarter wave. Is there a formula that you're using to get into that thing or somewhere?
Yeah, I mean,
I just divide the wavelength, if it's 4 into say 12 meters, 12 megacycles, then it would be 3, but that's not it. You got to keep more calculation to go in to get the answer.
well, you're looking at frequency, which is 1 over time. So you need to
Yeah.
divide that by the velocity of light, and that'll come out
Miles a
as,
second.
yeah, so they cancel each other, the seconds cancel each other out that way.
Yeah.
And you come out with units of distance.
Okay.
That way, that'll tell you how many meters long it is of one wavelength. And then from there, if it's a quarter wavelength, you divide it by 4, and then you multiply it by the velocity factor.
If you got the frequency as like 7 megacycles, that's considered 40 meters. And just then you can divide it by, if the quarter wavelength divided by 4, and you come up with 10 times 0.66. Is that workable? I mean, is it going to be a close enough answer for the test?
It'll be pretty close, although, the 40 meter band is actually a little bit closer to 41 meters.
That's why I asked if it'd be close enough for
Yeah.
the test.
So it may not be. So,
Okay, gotcha.
okay, which of the following can be calculated using a Smith chart?
Reed Baker.
Baker.
We're talking transmission lines with the Smith chart. What type of coordinate system is used in a Smith chart?
A.
B like in Delta. Resistance lines and reactance chords. Oh, what the hell is it then?
It's A.
Say,
Resistance circle. I thought it was a straight line for the resistance on the
Yeah.
Smith chart.
The resistance is, but you remember the reactants are gonna
Is
be
the arcs.
the arcs, yeah.
And what's the resistance? Is it a straight line in the Smith chart?
Yeah, the resistance is a straight line.
But that last question said no, I thought.
You can click on that question. It'll take us back, Chris.
That's all right. Forget it, guys. We got more to study than that.
Let's- Yeah, so you had said chords and it was actually an arc.
A resistant lines is what I was saying, but it's a, I guess the horizontal line is that, but then you got your circle lines going around that to give you where the resistance is.
Right.
I got you. Okay, forget it.
Which of the following is often determined using a Smith chart?
A,
Yeah. What are the two families of circles and arcs that make up a Smith chart?
A alpha, resistance and reactance.
Yeah.
A.
A,
A. Which of the following is a common use for a Smith chart?
C,
Okay, anybody else for another one?
I think it's A.
I would say B, the length and position and impedance matching.
I'm gonna say it's B.
Hmm.
Okay, in our Smith chart figure, what is the name of the large outer circle on which the reactance arcs terminate? So that's gonna be,
B like the Baker, the reactance axis.
yeah, the reactance axis. Okay, what is the only straight line shown?
I think we discussed this enough. B like in Baker.
Yeah,
Go ahead, Mike.
resistance.
Thank you, guys.
What is the process of normalization with regard to a Smith chart?
C,
I think it's B.
Yeah, it's gonna be B. What third family of circles is often added to a Smith chart during the process of solving problems?
Let's see.
C,
Yeah, SWR circles. What do the arcs on a Smith chart represent?
C,
D.
Yeah, delta. How are the wavelength scales on a Smith chart calibrated? Okay, we know we're talking transmission lines. And we're talking wavelength. So,
so
C,
C,
Charlie. Yeah.
whew, that Smith
Oh,
chart.
we didn't do too good on that one.
When constructing a beverage antenna, which of the following factors should be included in the design to achieve good performance at the desired frequency?
A.
Yeah, it should be at least one wavelength long. What is generally true for low band receiving antennas?
B,
Oh,
All of these, huh?
I think it's D.
It's going to be D. Yeah, the atmospheric noise in the lower
So
bands
high,
is so
yeah.
high that
Yeah,
the gain is not important. It's all about direction.
D.
What is the receiving directivity factor?
I see C like Charlie,
D,
forward gain compared to the reverse. Nope.
Either B or D.
D. D.
Actually, it's A.
Hey,
Like I said, it's A.
What is an advantage of placing a grounded electrostatic shield around a small loop direction finding antenna?
Oh, C.
Yeah.
C, yeah,
What is the main drawback of a small wire loop antenna for direction finding?
B,
Well, it does have
yeah,
a
it does.
defined null. Problem is it's got two nulls.
So it's A.
What is the triangulation method of direction finding?
D.
B, like,
Yeah. Multiple locations.
yeah,
Why is RF attenuation used when direction finding?
D,
B, like to reduce the, no, not the no. I guess D, increase, nope, low the bandwidth received to vent receiver. I thought it was be like in Baker, you're trying to get, no, if you get too close to the signal, you want to turn it down, else you get
Right.
great directions.
What is the function of a sense antenna?
S- C,
Nope.
That's going to be D. No, it's not.
it's A,
All right, it's A. What is a pennant antenna?
Like a flagpole, I like that one.
B.
Yeah, remember with a pennant, we're going to have a 900 ohm termination resistor. So how can the output voltage of a multi-turn receiving loop antenna be increased?
C, Charlie.
Yeah.
Yeah, number turns.
What feature of a cardioid pattern antenna makes it useful for direction finding?
That's the B Bravo. It has a very sharp peak.
C, Charlie.
C,
It's got the single sharp, but it's
No, not the
single
peak.
sharp.
Yeah. Yeah. Okay. 72.
I believe that's
You
it.
know what we need to study?
All right. So let's plan on next Tuesday. we can meet. What I would suggest at this point, you should start taking practice exams. If you've got an app for your phone or your tablet, that's a good way to practice. What you'll find is that you'll be able to get through a 50-question exam, in 15 minutes or so, 20 minutes. And what you should see is your scores starting to improve. It doesn't hurt to go back through the study guide again to see the question and the correct answer. The more times you see that, the more quickly you're going to associate that when you're actually taking the exam. So what I was thinking is next Tuesday, we can do a few practice exams together and see how we're doing. And we'll go ahead and finalize, do we need a special exam session, or do we want to go ahead and just plan on taking advantage of one of the ones that's regularly scheduled?
Hey, Chris, I think I had stepped out when y'all were talking about this before. I cannot make the one on the 15th if it's in the afternoon. If it's in the morning, I'm fine.
Okay, if that's a Saturday, then that would be.
No, I think that's a Monday.
Okay, Monday, it's at night.
Yeah, I can't make the 15th at night.
Okay. And actually, they would prefer to do something on a weekend just for availability of VEs to help proctor the exam. So
November the 6th works great for me, and I think Matt, if I'm recalling right.
Okay.
Problem with overloading the clubhouse, doesn't the calendar, when y'all put the calendar for the VE test, don't y'all know how many are coming for that test? Or else,
Yeah,
how do you?
the mask requirement got dropped. So, we can probably handle 8 to 10 people, which I think would take care of everybody.
I'm just saying, if 10 people that are not in our session right now come up and we put our 6 in it, that's gonna be 16. That's what I'm trying to get is, do they know who is coming to take a Saturday exam on their scheduled time, or they don't know? They can just show up and take the test.
You can generally just show up and take the test, but if we schedule something for a Saturday that's for this, you won't get bumped. You will be guaranteed a seat.
We can get together and schedule a Saturday that everybody can make or something if we want,
Right.
if we can do it.
Yeah.
Yeah.
So I'm going to talk to Don about it at the general meeting on Thursday, to let him know that we're thinking about that. I guess it would be the first Saturday in November.
What's the date? The 6th?
Yeah.
I can't make that. Sorry, guys. But like I said,
That's the first Saturday.
yeah.
Yeah, and Mike, if you can't make that,
No,
they've got the 15th coming up that Monday. If you wanted to take it then. I think it's,
Chris,
yeah.
on the, when you take the exam, what actual documents do you need? The FRN printed out, or just know the
You
the
need to know,
FRN?
you just need to know your FRN, and you're going to need an ID card, like your driver's license.
Okay, and you don't need a copy of the license that you currently have?
No,
Okay,
no. It doesn't hurt if you have it, but it's not necessary.
okay.
Because we can look up what your
2
current
lead
license.
pencils.
We actually provide pencils.
With erasers, huh?
with erasers. You're not allowed to bring in scratch paper. You can bring in a calculator, a standalone calculator, not the calculator on your phone.
We already discussed, guys, about bringing instructions for the calculator.
Yeah.
So it's probably not a
Yeah.
good idea to bring them.
So, any questions right now?
Oh, you said if you want a paper to like say work formulas with, you can write on the back of the test page.
Yeah, you
mentioned-
can write it on the back of the answer page. Generally, there's no more than 2 or 3 questions on the exam that would require a calculator.
The length of an antenna thing with all that.
Yeah. All right, well, I'm going to go ahead and stop.